I shall brief you on the conformational analysis of ethane molecule. Now, we know that we have seen in the last video that conformational analysis is an analysis of the energy changes that a molecule undergoes as the groups rotate about a single bond. Okay, and also it deals with the analysis of reactivity of various conformers. Right? So that's conformational analysis. Now here today we shall see the energy changes that happen to ethane molecule. Okay. Now to know the to carry out the conformational analysis or to do the conformational analysis, we need to the general method of writing the structure is the Newman projection. Okay. So we have got two conformations over here. Well, one over here is the Newman projection of the staggered ethane conformation, and this is the Newman projection of the eclipsed ethane conformation. Now in Newman projection, as you know, the carbon atom on the front is designated as a point, and the one with at the back is designated as the circle. Okay, and in staggered conformation, all the hydrogen atoms or the substituents attached to one carbon, the adjacent carbons are 180 degree apart, or the dihedral angle is 180 degree. And here the dihedral in eclipse conformation, the dihedral angle is 0 degree. So you can say that when the dihedral angle is 0 degree, we call it as an eclipsed conformation, and when the dihedral angle is 180 degree, we call it as a staggered conformation. All right. Now to understand more of the conformations of ethane, we shall take up the three-dimensional model of the Newman projection or three-dimensional model of the ethane molecule, and then carry out the rotations. Now, to understand the conformational analysis of ethane molecule, I am taking the help of a ChemTube 3D website, which gives us the structure of molecules in three dimensions. Okay, they explain the reaction structure of molecule using 3D models. So this is the website www.chemtube3d.com. Okay, you can explore this website. You get a lot of information regarding organic compounds. See here, you have got reactions, etc. In inorganic, you have the various structures, group elements, symmetry elements, etc. are shown beautifully using this, in this website. So you can explore this website, okay? Now, let's come back to our ethane molecule. Now, ethane molecule, here we have this ethane molecule which has a CC bond, single bond. Here you can see CC single bond, okay? And in this molecule, this is the ball and stick model of ethane molecule, and the big balls represent the carbon atom and the small ones represent the hydrogen atom. It is for easiness of explanation that they have colored the two hydrogen atoms, one green and the one on the other carbon as blue. Now we are going to explain the conformations with respect to this blue and green hydrogens. All right. This is the structure of ethane molecule, the Newman projection. Now this is the side view. Now coming to the front view, this is how it looks. Okay. Now this is here the dihedral angle across the single bond is what? It is 0 degree. And when the dihedral angle is 0 degree, we call it as the eclipsed conformation. All right. Now, free rotation is possible across this C single bond C, isn't it? When free rotation is possible, we get the dihedral angle changes. See, when the molecule rotates, the dihedral angle changes. Okay, so for every degree of the change in the dihedral angle, we get a different conformation. More clarity is possible when we bring these two carbon atoms one behind the other. Okay, see, you have different structures when the molecule rotates, right? And this rotation, the molecule continuously rotates. That's the beauty of it. The molecule keeps on rotating. Alright, now we shall see the various conformations happening when the dihedral angle changes. For easiness of explanation, we are going to explain the change in dihedral angle for every 60 degree, or the change in structure for every 60 degree change in the dihedral angle. So this is how the molecule is rotating. Okay, let us take up the eclipsed conformation. Now the dihedral angle is 0 degree. Alright, now we are going to rotate it to a 60 degree rotation. Now the dihedral angle between these two hydrogen is 60 degree. Alright, now you can see a different conformation, a different structure. Okay, now another 60 degree. Alright, we have got another conformation. Another 60 degree. Now this too can be considered as eclipsed, since all these hydrogen atoms, all these substituents on these two carbon atoms are hydrogen. It's the same compound what we had seen when the dihedral angle was 0 with respect to green and blue. Now the dihedral angle is 0 with respect to this green and white hydrogen, this blue and white hydrogen, these two white hydrogens, isn't it? And in each case, the structure is the same because it's all hydrogens. When the substituent changes, then we get a different conformation. Then we have to talk in terms of whichever substituent we have fixed to change the dihedral angle. Alright, so this is one sort of eclipsed conformation. Now here another, now what has happened? The dihedral angle between the green and the blue is 180 degree. So this is the staggered conformation. When the dihedral angle between the two substituents in reference, or the two planes which are in reference, is 180 degree, then we call it as a staggered conformation. Alright, now you rotate it again, you get another conformation, again you rotate it, get another get another conformation, one more rotation, another staggered conformation, you come back to the original. So you have rotated 360 degree now. Okay, and this rotation, as I said earlier, the rotation happens continuously. Okay, this rotation happens continuously. You can see here. Okay, so always the molecule keeps on rotating. Now we need to discuss the energy, difference in energy for the various conformations when the dihedral angle changes. Okay, so we need to discuss the energy profile diagram. Now it has been seen that it is this conformation when the dihedral angle is 0, they are highly energetic, they have high energy, or they are less stable. The molecule is less stable. Okay, but when the molecule here is when it is dihedral angle is 180, when all the substituents on adjacent carbon are 180 degree apart, then the molecule is highly stable. So in the case of ethane molecule, the eclipsed conformation is the least stable and the staggered conformation is the most stable. Okay, now accordingly we can draw the energy profile diagram. Okay, the energy profile diagram of the conformations of ethane molecule. We shall see how the energy profile diagram is the diagram appears when the molecule keeps on rotating and we get various conformations. Alright, Let us check out the energy profile diagram. This is the energy profile diagram of the various conformations of ethane molecule. Now, energy profile diagram of the conformations is the plot between the energy of the molecule and dihedral angle. That is the angle of rotation of the reference atoms. Now, in the case of ethane, here in this picture, these two hydrogens, the hydrogens which are in red, are considered as the reference hydrogens. Okay, just for an easy understanding, let's consider these two hydrogen as the reference hydrogen. Now, what we are going to do to carry out conformational analysis, we know that conformational analysis deals with the energy variation when the dihedral angle changes. Okay, now let us take initially, let the dihedral angle be 0 degree. So when the dihedral angle is 0 degree, these two reference hydrogens will be close together, right? I don't have the picture of that form. Eclipsed, it will be the eclipsed form. These two red hydrogens will be here, close together. Here you can see instead of that red and blue. But these two red hydrogens will be close together when the dihedral angle is 0 degree. Now, as you increase the dihedral angle, what happens? This molecule, or the energy of the molecule, comes down. The energy of the molecule comes down and then it reaches a minima when the dihedral angle between the reference hydrogen is 60 degree. Now at this point you can see that all the hydrogen atoms on the adjacent carbon atoms are anti to each other, opposite to each other. Though the dihedral angle between the reference hydrogen is 60 degree, all the hydrogen atoms are anti to each other. You can see here this red hydrogen is almost anti to this blue hydrogen, that is almost 180 degree apart. Okay, so the energy is minimum here. Now when you increase the dihedral angle, what happens? This hydrogen, the reference hydrogen over here, moves closer to this blue hydrogen, right? So what happens? The energy slowly increases, and it increases and reaches a maxima when the hydrogens are placed close to each other, to the closest point to each other, and that's at 120 degree, when the dihedral angle is 120 degree. Of the dihedral angle between the reference hydrogens is 120 degree. So that's the eclipsed form. Again, you increase the dihedral angle, what happens? This hydrogen starts moving apart. Okay, so the energy comes down. And it reaches a minima when the dihedral angle is 180 degree. At this point, these the two reference hydrogens are at 180 degree, are 180 degree apart. And of course, all the hydrogens are anti to each other, or 180 degree apart. So this continues. Again, you increase the dihedral angle, the energy of the molecule increases, reaches a maxima. It will be the eclipsed form. Again, you increase the dihedral angle, it reaches a minima at 300 degree angle. It will be the staggered form. You increase the dihedral angle and you complete one rotation. When you reach the 360 degree rotation, you again arrive at the eclipsed form. These two hydrogen will be close together again. Okay, so there is a minima and a maxima. There is a minimum energy, molecule has a minimum energy and the molecule has a maximum energy. Now this difference between the energy of the, difference between the energy of staggered and eclipse is around 12.1 kilojoules per mole, or around 3.3 kilocalories per mole. Okay, that means eclipsed is less stable than staggered, because staggered has got minimum energy, lesser energy. Okay, almost 12.1 kilojoules lesser than the eclipsed energy. Okay, but still there will be free rotation. Free rotation continues, but there will be an energy barrier for free rotation from staggered to eclipsed. And spectral studies have shown that more than 99% of the molecule will remain in the staggered conformation. So that implies when the molecule reaches the eclipsed conformation, it quickly comes down to the staggered conformation. Okay, rate of interconversion, or the rate of conversion from the eclipse to the stagger will be at a faster rate, or the rate of free rotation from the eclipse to the stagger will be faster. Now, as you increase the temperature, the interconversion also becomes rapid because the molecule as such gains kinetic energy. Now, every point on this plot, on this energy profile diagram, represent a conformation. Okay, so we have seen for every infinitesimal change in the dihedral angle, the structure of the molecule will be different, and so it can be considered as a conformation. So there will be infinite number of conformation across this plot when you move or change the dihedral angle from 0 degree to 360 degree. But all these conformations are not called conformers. Only those conformations which has got minimum energy are called conformers. Okay, that means the conformation which lie in the minima of the profile, energy profile diagram, are called conformer. So in this case, the staggered conformation is the conformer. Eclipse conformation is not a conformer. Okay, this you have to keep in mind, this terminology. You don't use the term conformer for an eclipsed conformation. You use a conformer only for the staggered conformation of the ethane molecule. Okay, so eclipsed is not a conformer, staggered is a conformer. So you can say that all conformations are not conformer, but all conformers are conformations. Staggered is a conformation. It is a conformer too. Eclipsed is a conformation, but it is not a conformer. Hope you got the point. Alright, now why is that you have difference in energy for staggered and eclipse? There is almost 12.1 kilojoules variation, difference of 12.1 kilojoules of energy between the staggered and eclipsed. Now, what is the reason for this energy barrier? Now, the energy barrier for rotation, we shall discuss the various energy barrier for the rotation. Now, here you have the diagram which shows the you have the staggered conformation over here and the eclipsed conformation over here. Now, when the molecule moves from the staggered to the eclipsed over a 60-degree rotation, the ethane molecule, all the hydrogen atoms come closer to, will be at its closest point. At this point, there will be an increase of 4 kilojoules per mole at every point. So altogether, there will be around 12 kilojoules per mole of increase in energy, or 2.9 kilocalories per mole increase in energy. Now we need to see why this 12.1 kilojoules of mole increase in energy is there between the staggered and eclipsed. Okay, now this is, there are two reasons which has been attributed for this increase in energy. They are steric strain or steric repulsion and torsional strain. Okay, steric repulsion and torsional strain. Now, steric repulsion is also called as van der Waals repulsion. Now, we'll see what is steric repulsion and torsional strain. We can explain van der Waals repulsion in this way. Now, we have the two Newman projection for eclipse conformation and the staggered conformation. In the eclipse conformation, the two hydrogen all the hydrogen atoms are at its closest point. So you can see here the hydrogen atom, the molecule, there will be a van der Waals repulsion, a steric repulsion, because the atoms will be closer to each other. So the possibility of the atom overlap is coming nearer to each other is possible. Okay, now this strain, that is the steric repulsion, contributes only 10% towards the instability of the eclipsed form because of the small size of the hydrogen atom. Not much effect is there. Okay, but the major reason for the instability of the eclipsed conformation of the ethane molecule is due to the torsional strain or bond opposition strain. Now this strain, the torsional strain, arises due to the repulsion of the bonding electrons, okay, in the CH bond when they come closer. Now you have this eclipsed structure. These CH bonds are nearer to each other, so you have this wedge form of representation. So this CH and this CH are closer to each other. So in the Newman projection, it's much more clearer. Okay. Now when we mark the orbitals, these two orbitals are filled orbitals. Okay, filled sigma orbitals. So there will be electron cloud around this orbital, in this orbital, and hence this electron cloud will repel each other. Okay, this is the reason for the major reason for the energy increase in the eclipse conformation. Okay, now, but in the case of what you call the staggered conformer, wherein the energy hydrogen which are in reference are opposite to each other, anti to each other, the dihedral angle is 180 degree. You can see here the filled orbitals are anti to each other, 180 degree apart. Okay, but at the same time, nearer to the filled orbital of one hydrogen, there is an unfilled orbital, unfilled anti-bonding sigma star orbital. Now these two orbitals will cause a stabilizing interaction. A stabilizing interaction will arise between the filled CH sigma orbital and the sigma bonding orbital and the empty CH sigma star anti-bonding orbital. So they will contribute to the stabilizing effect of the staggered conformer. That's because the electrons in the filled orbital can move from the filled orbital to the unfilled antibonding orbital. So because of this electron diffusion or electron dissipation, the molecule will be stabilized. So these are the two reasons for the increase in energy of the eclipsed conformation when compared to the staggered conformer of the ethane molecule. Okay, so steric repulsion and torsional strain. Steric repulsion arises due to the size, atom size. Okay, when the atoms in reference interact, while torsional strain is because of the repulsion between the electron cloud in the bond. Okay, in this case it is the CH bond. Alright, so hope this is clear to you, the energy profile diagram and the reason for the energy variation. If you still have any clarifications or doubts, please feel free to ask. Thank you.